Hey group, welcome back to Miss J's Chemistry Kitchen. You haven't seen a demonstration in my kitchen for a while. Thought I'd do this one from home because I didn't want to mess up my new clean classroom before hybrid. I'm going to show you the demonstration that goes along with the rate law lab that we're going to be performing when you get back hybrid, or you're going to get data from the people that are back in the lab for you to process. So this lab starts with one of the reactants being what we call Genetian violet. And you can buy this at the pharmacy. It's used to either disinfect a cut or a sore, but it can also be used to cure yeast infections, especially in your mouth. So this is the stuff that I'm going to use here. You're not going to use the stuff that you can buy at a pharmacy because it contains alcohol. It doesn't really matter for the demonstration purposes. You're going to use a stock solution that I create. But here's the Genetian violet. It's also called crystal violet. And it only takes a drop, one drop from this little bottle in about 125 milliliters of water to turn that water that beautiful crystal violet color. Then the other reagent for this lab is going to be sodium hydroxide. And it's going to be a much higher concentration than the Genetian or crystal violet. So I'm going to show you what happens with this reaction. When I add these two things together, it's a simple synthesis reaction where the hydroxyl or hydroxide group will hook itself onto the really long carbon chain that makes up crystal violet. So I've got not a beaker here. I've got a canning jar. I've got to remember to not can stuff in this jar after this. And I'm going to pour some of the solution that I pre-made into here, and I'm going to keep some so you can compare. This is not technical at all. I'm not measuring. This is just me pouring stuff together. So what I'm going to do is I'm going to pour some amount, I'm not measuring, sodium hydroxide, 1 molar, into the jar. And I want you to watch what happens here, where you're going to see that the color in the jar is going to start to get lighter over time. So what you're noticing is the crystal violet starts out purple, but the new product with the hydroxyl attached to the crystal violet is clear. And it takes time for that reaction to occur. If we can figure out the absorbance of light that is hitting this solution, and then we can see how the absorbance will change over time, this will correlate directly to the change in concentration over time, and therefore we can come up with a rate law. So I've been talking here for about 30 seconds, and you can see it's gotten substantially lighter as I have been talking. And we're going to measure how long it's going to take to get as light as possible. You're going to do this using a colorimeter or a SpectraVis analysis tool that I'm going to show you next. Okay, so here's your setup for how to measure the difference of absorbance per time using a SpectraVis. So hopefully you have uploaded the extension to the SpectraVis extension onto your Chromebook. And when you get to the lab, this is going to be the SpectraVis that you may use. If you are using a colorimeter instead, pretty much the setup will be the exact same way. So this one does not use the LabQuest Mini. This one plugs in directly to your computer. That's why we had to upload that extension. Then what we got here is some selections to make. You will see the third selection down says absorbance versus time. And I'm going to talk for a minute here about what we mean by absorbance. So light is either absorbed by a color or transmitted through something of a particular color. Purple will absorb green light. So if I can measure how much green light the crystal violet initially absorbs and then see how that changes over time, that will correlate directly to concentration. So I'm going to select here absorbance versus time kinetics. And it's going to tell me to wait 17 seconds for the lamp to warm up. This is something I have already done prior to making this video, so I'm just going to X that out. Now, in the settings button, you will see calibrate. I guess we still need to have the lamp wait up. We're just going to hang out and let it wait for about 13 seconds. I know dead time in videos is a little frustrating. Okay, so really important about cuvettes. Cuvettes are clear little plastic boxes, and because we want to measure how much light goes through them, it's really important that we don't put our fingers on the side, because if we put our fingers on the side, we leave smudges, and that will also absorb light. So you always handle a cuvette by the edges, and you should always wipe it down with a paper towel before you put it into the SpectraViz. So the first one is filled with just distilled water, because distilled water is perfectly clear, and if it's perfectly clear, it will absorb no light. It gets stuck right there in the SpectraViz just like that, and then we hit finish calibration. And there it goes calibrating. And you'll see at the bottom right-hand side of the screen that the distilled water is absorbing no light, which is exactly what we want. Grab it by the side and pull it out gently. Then, this is the next piece. Here I've got some crystal violet solution. I'm going to pre-make this for you. It's going to have a concentration of 0.00025 moles per liter. This one doesn't. This is just for demonstration purposes. And you are going to mix a 2 molar solution of sodium hydroxide with it with a particular volume. My particular volume is not going to be exact because this is for demonstration purposes. And then quickly, what you're going to do is grab a new cuvette. You are going to quickly get a dropper, transfer from the solution into the cuvette as quickly as possible, and you will have a better way of doing this if you're not at my house. And then you're going to quickly, by the edges, put that right there in the SpectraViz and hit collect. And the wavelength that I'm going to choose is 565 nanometers. Okay, so here's what it looks like after I've collected the data. Vernier doesn't do the greatest job of graphing, but there are some important components to what you're looking at here that we can notice. In the upper left-hand corner, this little graph just shows that where we are collecting the data at. We're collecting the data at a wavelength of 565 nanometers. If I was to blow this up, you'd see that this is the highest peak of absorbance, which, since purple absorbs green light, we're doing it correctly. Next piece here is checking out our data. And as the purple diminished and the clear liquid became apparent, my absorbance should have decreased. And I'm taking a look here, besides a few little anomalies here and there, which are going to happen because the liquid shifts inside the SpectraViz and so on and so forth. But the trend is definitely decreasing, and you can also see that in the graph. Now what I want to do is I want to be able to really analyze this data. So to do that, I need to copy this into Google Sheets or Excel if you wanted to. And I could save this file as a CSV, but it turns into a kind of a pain. So what I like to do instead is I like to highlight the data and just copy it and paste it directly into Google Sheets. If I click on the labels of the table, it highlights it all for me. I collected this for 98 seconds. You will probably do about the same amount until it starts to level off. I hit Control C for copy, and then I will paste it directly into a Google Sheet. And notice that on Vernier, it didn't take it out to so many decimal places, but once we transfer it, it gets a little bit more precise. So we like that. Now we practice our graphing skills. We highlight both columns. We insert a graph or hit this icon right here. And we want a scatter chart. We want a scatter chart, and to fix this, we need to add the x-axis, and we want it to only graph from x-axis being in the A column to y-axis being in the B column. And we got that there like that. Now, we have to refer back to Learning Target 14, where we've got a set of data that we want to decide if it's zero order, first order, or second order. Recall from Learning Target 14 that if we graph concentration versus time and the graph is linear, we know that it's zero order. So let's check that out. I'm going to hit Series. I'm going to make sure that I choose my trend line. I'm going to say that it's linear, and I'm going to apply an R-squared value. And 0.91 for my R-squared value, 91% of the data falls on that trend. Let's see if we can get something closer. Now, I know that to do first order reactions, the natural log of the concentration versus time would be a straight line. And I know for second order, the inverse of concentration versus time would be a straight line. So at this point in time, to not give away the rest of this lab, I'm going to let you play around with it, play around with your data, and attempt to decide if the reaction of sodium hydroxide to crystal violet is zero order, first order, and second order, using the evidence that you gathered during the course of the lab, not looking up the answer on the internet. So the write-up for this lab is going to be very simple. What you're going to do is you're going to clean up your data table, clean up your graph, show your work, and answer the questions. People who are in the lab hybrid are going to share their raw data, Excel or Google Sheets document with the people that are at home. And the people at home will be tasked with watching this video, maybe calling in and giving moral support to the people who are doing the lab during class, and then processing this data on your own. So hopefully this was helpful. I will see you all on Thursday.